Right now, thousands of people could be reading the exact same row in a database at the exact same moment someone else is updating it. No errors, no waiting, no corrupted data. How? It sounds completely impossible when you first hear it. I mean, think about it for a second. If you and 1,000 other people are all trying to view and alter the exact same piece of digital information simultaneously, chaos should absolutely ensue. Systems should crash, screens should freeze, data should just vanish into thin air. But it doesn't. The internet hums along perfectly. Every single time you buy a plane ticket, check your bank balance, or add an item to a digital cart, you're relying on a massive feat of engineering. And it all happens entirely behind the scenes, totally invisible to us. In this explainer, we're going to break down the exact mechanism that makes this modern miracle possible. By the end of this, you'll understand precisely how databases pull off this magic trick every single second of every single day. To truly understand the solution, we first have to set up the problem from complete scratch. Databases are relentlessly bombarded with requests. You have constant, heavy traffic. People are reading data, they're writing data, they're updating profiles. We call these individual actions transactions. The fundamental job of a database is to process all these transactions at the exact same time without them tripping over each other. This absolute requirement is called isolation. Isolation simply means making sure database transactions running at the same time don't interfere with each other. Think about how often you rely on this without even noticing. Imagine you're trying to buy the very last aisle seat on an airplane at the exact same millisecond as someone across the country. You're competing with hundreds of people for that one single spot. Without proper isolation, the system might accidentally sell that single seat to both of you. You'd show up at the airport and someone else is sitting in your spot. The database has to guarantee that every single transaction acts as if it's the only one happening in the entire system, even when thousands of others are running right alongside it. Okay, let's dive into this and look at the most obvious way you might try to solve this isolation problem. The simplest, most naive approach is simple locking. It works just like a lock on a fitting room door. A transaction comes along, it wants to read a row of data, so it locks it. Any other transaction that wants to write to that row just has to wait outside. Then, step 3 happens. Massive queues start to form. And finally, step 4. The throughput of your entire system completely collapses. Under real-world internet traffic, you don't just have 1 or 2 people waiting. You have thousands. And if they're all locking rows of data just to read them, nobody can write anything. The entire system basically grinds to a halt. Readers block writers, writers block readers, everything stops. Simple locking completely fails to scale when you throw real heavy traffic at it. To really visualize the pain of this simple locking approach, think of it this way. Lock-based isolation is like a library with only 1 copy of each book. A line forms behind anyone reading it. If someone is sitting there reading the newest bestseller, no one else can even look at it until they're completely finished. And that includes someone who maybe just wants to quickly grab the book to fix a typo on one of the pages. In a busy library, a massive line forms right out the door behind every popular book. People get frustrated, they wait for hours, and the library becomes completely useless to the vast majority of its visitors. This is the exact bottleneck early databases faced. They desperately needed a way to let people read the book while someone else was actively editing it, and they needed to do it without anyone seeing half-finished sentences. The brilliant solution to this massive bottleneck is an engineering concept called multi-version concurrency control, or MVCC for short. The core mechanism of MVCC is wonderfully simple once you grasp it. The golden rule is this: never overwrite data in place. When a transaction updates a row in the database, it doesn't delete or change the existing data. Instead, it creates a completely new version of that row. The database intentionally keeps the old version around untouched. Then it tags the new version with the unique ID of the transaction that created it. It's kind of like putting a sticky note on the new version that says, created by transaction 500. So a row in an MVCC database is no longer just a single static piece of information. It actually becomes a living, breathing timeline of different versions. And all of these versions exist simultaneously inside the system. Let's go back to our library analogy to make this incredibly intuitive. MVCC is a library that photocopies a book instead of editing the original. Readers read old copies, writers edit new copies. If you want to read the book, the librarian just hands you a photocopy from this morning. You can sit in the corner and read it in total peace. Meanwhile, if someone else wants to make an edit to that exact same book, they don't rip the pages out of your hands. They just create a brand new photocopy at the front desk, make their edits there, and file it away. You, the reader, keep reading your old copy entirely undisturbed. The writer edits their new copy. Nobody waits in line. Nobody sees a book being awkwardly edited mid-sentence. You've completely separated the readers from the writers. Now, what's really interesting about this slide is how the database manages all these different photocopies. If there are suddenly 10 different versions of the exact same row of data, how does the system know which one to show you? Well, it does this through a mechanism called snapshots. When a transaction begins, the database hands it a snapshot. You can think of a snapshot as a perfectly consistent view of the entire database from the exact fraction of a second that your transaction started. You don't just see the latest, messy data. You see whichever version of a row was the most recently finished and committed version at the exact moment your snapshot was created. Anything that happens after your snapshot is completely invisible to you. A snapshot is like a photograph of a busy street at 3 p.m. It's a frozen, consistent moment, even if you study it for an hour. Once you take that picture, it is frozen in time. You can sit down and study that photograph for an entire hour. You can count the cars, you can look at the people on the sidewalk. And during that hour, the real street outside is still moving. Cars are driving away, people are walking into stores, the weather might even change. But your photograph, it never changes. None of that new activity appears on the paper in your hands. You're looking at a frozen, perfectly consistent moment in time, no matter how much time passes while you examine it. That is exactly how a database transaction views data in an MVCC system. Let's walk through this timeline to see exactly how powerful this is in practice. Imagine you need to run a massive, heavy report that scans an entire database table. At 0 seconds, your report query starts and the database takes your snapshot. Now, scanning this massive table takes time. At 10 seconds in, thousands of background transactions are busy updating user profiles and changing data all over the place. At 20 seconds, even more background writes occur. New rows are added, old ones are deleted by other users. But finally, at 30 seconds, your report query finishes. Because of your snapshot, your query completely ignored all the chaos happening at 10 and 20 seconds. It read a pristine, perfectly consistent version of the data exactly as it was at 0 seconds. The math in your report will be flawlessly accurate, totally untouched by the frantic modifications happening in the background. So, the crucial point is this. Readers never block writers, and writers never block readers. Because readers are happily working from their own frozen snapshots of old versions, they never ever need to wait for a writer to finish doing their job. The writer is just creating a brand new version in the background. They aren't touching the old version the reader is currently using, and the exact same goes the other way around. A writer doesn't need to wait for readers to finish. Why? Because the writer isn't modifying the specific version those readers are looking at. This is the exact answer to the scenario we open this explainer with. This is how thousands of people can read a row while someone else updates it with 0 errors and 0 waiting. But as with all great engineering marvels, nothing is entirely free. There's a reality to the system we absolutely have to talk about. The big trade-off for all this magic is table bloat. Think about it. If you're constantly creating new versions of rows every single time an update happens, and you're keeping all the old versions around, your database is going to get heavy, very heavy. Old row versions that no active transaction needs to look at anymore just become dead weight. They sit there, they consume massive amounts of disk space, and worst of all, they force the database to work harder and slower when it tries to scan through tables. Suddenly, that instant web page load takes 5 seconds, then 10. And this brilliantly illustrates how databases are designed to clean up after themselves to solve that exact bloat problem. They use a mechanism called vacuum. Vacuum is an automated background process running constantly inside the database. Its entire job is to hunt down and identify those old, dead row versions that are no longer visible to any currently active transaction. Once it finds them, it cleans them up. It reclaims that disk space so it can be used for new data. It's an absolutely vital piece of database maintenance that keeps the whole system running fast and smooth. To stick with our library, vacuum is like a library janitor periodically walking through and recycling old photocopies that nobody's reading anymore. This keeps the library shelves neat and prevents them from overflowing. But there is a huge operational catch here. If a visitor comes into the library, grabs a photocopy, and then falls asleep at the desk for 3 months, the janitor is not allowed to recycle that copy, or any copies related to it. If a transaction stays open for far too long, it literally holds that snapshot open. The database can't clean up the old versions, the janitor gets stuck, and your hard drives rapidly fill up with bloat. If this is the kind of content you want more of, subscribing takes 1 second and it genuinely helps the channel grow. Now that we understand the pure theory, Section 15, Real-World Implementations, PostgreSQL versus MySQL, let's look at how the biggest database engines in the world actually build this system. Let's move to Cassandra and see how this builds out in a direct comparison. On the left, we have Postgres. Postgres stores all of its old row versions directly inside the main table itself, which it calls the heap. Because everything is just mixed together, it heavily relies on that vacuum process we just talked about. The main risk here is extreme table bloat if vacuum falls behind. If you leave a transaction open too long, vacuum is blocked, and the bloat grows right in your main storage. Now, on the right, look at MySQL, specifically its default InnoDB engine. MySQL takes a totally different route. It only keeps the absolute latest version of a row in the main table. It takes all the older versions and shoves them into a completely separate storage area called the undo log. Its cleanup mechanism is an automatic undo purge. So the main risk isn't table bloat. It's the growth of this separate undo log. If a long transaction hangs open in MySQL, the undo log can't be purged, and that specific log file grows massively. Two different engineering choices, both achieving the exact same MVCC magic. Which brings us completely full circle back to our opening question. Thousands of people reading the exact same row at the exact same moment someone else is updating it. No errors, no waiting, no corrupted data. How? Well, you now possess the exact knowledge of how that impossible scenario works. It works because databases never overwrite data in place. They create new versions. They hand every user a perfectly frozen, consistent snapshot of the data, completely separating the readers from the writers. Next time you click a button and a digital system responds instantly, while millions of others are doing the exact same thing, ask yourself what invisible mechanisms are working in the background to hand you your perfect snapshot of reality. And more importantly, what happens when those incredibly complex systems are pushed to their absolute breaking points by artificial intelligence? But that is a topic for another day.